Welcome. In this lesson, we'll take a look at section 3.3 with antiderivatives of functions. And we're going to be using some rules, mainly the power rule for antiderivatives in this lesson. So two objectives for this video are going to be finding antiderivatives using integration rules, and then finding the antiderivative of an indefinite integral. So let's consider the first couple examples here that take a look at finding the antiderivative. We call that capital F of x of each of the functions. So if I wanted to take an antiderivative, I first want to kind of remember some of the derivative rules that I've learned in the past. So if I have just the derivative of, say, a power term, x to the n, notice that we would just bring down the power as n and raise my variable to the n minus 1. That was our derivative rule for just power terms. Now, if I considered walking this back in reverse, when I take an antiderivative, I really want to go, again, in the reverse order. So let's just notice what things happened for this power rule to take place. So two things happened. One was I multiplied by the current power, and two, I raised x to the n minus 1 power, or subtracted 1 from the power. So if I consider doing something like this in reverse, well, I want to first consider actually adding 1 to the power. So when I consider an antiderivative, in this case, I want to consider, well, instead of subtracting 1 from the power, I actually want to add 1 to the power. The power of x specifically. And then instead of multiplying by the current power, I'm going to divide by the new power. So we'll divide by the new power. So if we think of it in terms of those operations, we're really going to just do those in reverse, and that will kind of pull back our derivative back to its original function before the derivative. So we call this f, capital F of x. And again, just to recall, the derivative of this capital F of x is little f. So we can actually double check this result when we're done to just verify that we do have the true antiderivative. So for each of these individual terms, I'm going to try to, again, consider adding 1 to the power of x, and then we'll divide by that new power, and then we'll see if we've got the right antiderivative. So for this first term, we can take that 3x to the 4th, and we'll just make that 3x to the 5th, adding 1 to the power, and we'll divide by the new power. And then for the second term, we have 2x, and I'm going to add 1 to the power, which would make 2x squared, and then again divide by that new power. So those two steps, add 1 to the exponent, or the power of x, and divide by that new power. So certainly we can go ahead and just simplify this just a little bit. For capital F of x, we have 3/5 times x to the 5th, and then plus x squared. So I think this is looking good for a one antiderivative. This is one possible result for an antiderivative. Certainly we could have here any constant we actually want on the end of this, and this would be a valid antiderivative. If we considered going and checking this, we can take this capital F prime and just make sure that we get back to our original function. Again, with any constant on the end, that constant value is just going to go to 0 and it's going to disappear. So if I considered the power rule here, I could say bring down my 5, that'll cancel out with the divisor of the 5, and we'll just have 3x to the 4th again, looks like, plus we have 2 times x, and then the constant again can go away. So when we add that plus c, we're just saying we can have any constant value on the end of that function, and it would still be a valid antiderivative. So I think that checks out with that method. Let's go ahead and try the second one in part B. We have a part B that is 5x to the 3rd and then plus 1 over x squared. So I might first consider just rewriting this as 5x to the 3rd and then plus x raised to the negative 2nd power. This way I can kind of utilize that power of x to my advantage when I go to take the antiderivative. So we'll go for capital F of x, the antiderivative. First we can add 1 to the power, which would be 5x to the 4th, and then divide by the new power of 4. Next, we'll do the same thing for x to the negative 2nd power. So we will add 1 to the power, that would be negative 1, and then we'll divide by that new power. So that is negative 1 here. So simplifying this antiderivative, again, we could have here a plus c on the end. Any constant would work on the end of this, would characterize any antiderivative, again, where c here is any constant. And my final capital F function here, if we wanted to simplify this just a little bit to make it cleaner, we have 5 fourths times x to the 4th, and then minus, this would be 1 over x. X to the negative 1 is always just 1 over x, and we just have that negative constant. Again, with our plus c, that would finish out that antiderivative, where again, c is any constant, would be a valid antiderivative. So there's your capital F of x antiderivatives for a couple questions. We'll continue this trend of taking antiderivatives, and we'll take a look at some indefinite integrals and work in the notation for our indefinite integrals. So let's start with our part A here, dropping down. We want to take the indefinite integral. Notice that in these questions, the integral has no bounds. Therefore, when we're done, we should still have a function of x. It's really going to be our capital F function left over. So let's consider antiderivative for both all three of these terms in the question. We have x cubed becomes x to the 4th over 4, adding 1 to the exponent and dividing by that new exponent. We have negative 4x squared divided by the new power 2. And then finally plus 1 here. Well, we really can imagine that there's like an x to the 0 sitting there. There's no x terms there, but if we added 1 power to the x, we'd simply just get 1 times x. And then we can finish this off with a plus c. Certainly we can divide that 4 over 2 and become just a 2 there. So I'm just going to erase here and rewrite that as a 2. And we should be ready to go. Just as a 2. Perfect. So that would be the indefinite integral for part A. We'll go ahead and just go through the letters here. Part B takes a look at the square root function. So again, here's a great opportunity to rewrite this before we take our antiderivative. So we could say that's equivalent to the integral of x raised to the 1/2 power dx. So same rules apply for that kind of antiderivative power rule there. Would be we want to take x and add 1 to the exponent, making it 3/2, and then we'll divide by that new power 3/2. And then add our constant c. So taking a reciprocal of our powers here, the final result we could say would be 2 times x raised to the 3/2 over 3, and then plus the c. That could be our antiderivative there. Part C, we have an exponential function and another root function to take a look at. If we recall, the exponential function is its own derivative. And so when I go to consider its antiderivative, well, it's also going to just be its own antiderivative. There's no change in the exponential in either direction. So let's go ahead and maybe rewrite this portion. We could say this is 5, and then square root of x cubed, we could say is really x raised to the 3/2 power to start. I'll just kind of remind us up there. So if I have a constant times e to the x, again, this term doesn't change. The 4 constant stays. E raised to the x would stay the same, so there's no changes with that. And now let's consider the second term. We have plus 5. We'll have x raised to the 5/2. That would be 3/2 plus 1. And then we could divide by that new power, 5 over 2. If we add that plus c, we should have a complete answer there. I'm going to clean this up just with our reciprocal for that function, or the denominator there. So if I multiplied by 2 over 5 in both the numerator and denominator there, looks like our 5's will cancel here in the numerator, and we'll just have 2 as a constant. So let's rewrite that cleanly here, 4e to the x, and then we'll just have a plus 2 x raised to the 5/2 plus the constant c. If we move up, we'll take a look at part D as well. Part D takes a look at a exponential base 5. So let's go ahead and maybe think back to our derivative for this type of function. If I had the derivative of a exponential base b, I'll just say 5 raised to the x just for sake of example, same idea. Well, for this derivative, for every exponential, we would say rewrite my exponential 5 raised to the x times the natural log of our base, in this case 5. So if I had to multiply by that natural log of the base to get a derivative, well, it would make sense if I wanted to get to the reverse order. If I wanted to go backwards, I'd have to divide by that same natural log of the base. And that would actually be good intuition for our antiderivative here. So we could say that the antiderivative for any exponential term, base b, is that function 5 raised to the x divided by the natural log of the base. And then again, plus c. If we ended up taking the derivative of this function here, if I took the derivative of 5 to the x over ln 5, I could kind of confirm this just with a quick derivative to make sure I get back to my original. ln 5 is just a constant, so when I take the derivative, I'll have the ln 5 is just a constant. I'll pull that out, 1 over ln 5. And then the derivative for 5 to the x power is sitting right above, so that would be 5 to the x power ln 5 again. And we'll notice that those natural logs will cancel and just be left with that original 5 raised to the x. And that's exactly what we want to see. Part E, this is more of maybe a reminder from our previous lesson. We actually know this from one of the problems that we did, that the integral of 1 over x has an antiderivative here of natural log. If we recall the derivative for the natural log, this is a special case here. The derivative of the natural log function we call just 1 over the argument x. And so if I wanted to go in the reverse order, the antiderivative for 1 over x would again be the natural log function. So here we could say that this integral is the natural log of x plus some constant c. Part F looks a little complex because of a quotient here, but whenever we are placed with some quotient, it's a good idea to just consider, could we simplify this before taking an antiderivative to make it less complicated? And in this case, I think we can break this down just with some algebra on the front end. So I'm going to consider just dividing each of my 3 numerator terms by this x quantity and see where I get. So this would be equivalent to the integral of x to the 5th over x would just be x to the 4th, minus, we have 3x squared divided by that x would just be a single x left over, and then plus 6 here would just be a divisor here of x, so 6 over x. And then we have the dx. So there's my integral with just 3 terms, which I think we can handle quite well with our power rule. Another point to make here is the 6 over x. This is really similar to what we've seen before. This is just 6 and then x raised to the negative first. So if we go to get this done with the power rule, we can say this is just going to be x raised to the 5th, add 1 to the power, divide by my new power of 5. Then we can subtract 3 and then x squared over 2. And then the final one is if we add 1 to the power, notice that we would get 0 for this power. So this really is the equivalent to 6 times 1 over x. So maybe in this case it would have been better to just keep it as is, but this kind of shows us that there's just a constant times 1 over x, which we would see as just adding 6 as a constant multiplier times the antiderivative for the 1 over x term we just saw in the previous problem was just the natural log. And this would actually be a natural log of absolute value x, so let's make that change there. Just notice that. So we should have a natural log of the absolute value of x. Because certainly when we take this integral, the value of that natural log cannot be negative. So to make sure that we don't do that, we'll have to have an absolute value in that natural log. We'll finish that out with that plus c, and we will conclude with that. So there we go. That would be part F. All right, we're going to take a look at applying again the fundamental theorem of calculus, but this time now that we know our antiderivatives, or at least enough antiderivative rules to consider these, we can tackle these through the whole problem. So let's take a look at part A. Again, we notice that there might be some opportunities here to simplify this integral first before trying to evaluate the antiderivative. So when we consider this, looks like I'm going to rewrite this. This is, again, a definite integral because we do have bounds now, 1 and 3. 1 and 3 are our bounds. There we go. And so I'm going to first focus on, again, we can copy this bounds 1 to 3. This is the integral still. And now I'm going to consider how I can rewrite this function. If I divide each of these terms by x squared, I can consider this as 2 times x will be left in the first term. And then the second term we could rewrite as plus 7 divided by x. And that dx. So it looks kind of similar to what we had in our previous problem, but now we have the added component of actually a definite integral with bounds. So let's walk through that process. So first, I'm just going to go out and try to solve for kind of that capital F, or the antiderivative of the function. And so I do that by, again, taking our antiderivative. This would be 2x quantity squared divided by 2. And then we can say that the second portion is just going to be 7, and then 1 over x itself is just going to be the natural log of absolute value x. Now that we have our antiderivative here, I'm going to leave off that plus c because we actually don't need it when we're considering these definite integrals. So this is really the capital F function that we have right here. Now I'm going to consider evaluating this capital F function now at my two endpoints. So if this is capital F, I'm going to consider the fundamental theorem would say find capital F at your B endpoint, subtract capital F at A. That would be kind of the definition of how I would walk out this integral. But I know my B and my A now, so let's replace those. B, we go here, is going to be the 3, and A is 1. So what we're actually calculating here is going to be capital F of 3 minus capital F of 1, and I've just found my antiderivative. So we can go ahead and try this out. So certainly when we look at capital F of x, these 2's in the front, we can cancel those and we'll just have x squared. So let's apply our fundamental theorem. Again, we'll evaluate the first 3. So we have x squared, which would be 3 squared, or 9, plus 7 times the natural log of absolute value 3 would still just be 3. Subtract, we'll do the evaluation at 1. 1 squared would be just 1. Plus, we'll take, as again, 7 times the natural log of 1. Okay. And let's see if we can simplify this, and we'll just keep this within the natural log format here. So we have 9 plus 7 ln 3. If we subtract here, notice that we'll have a subtract 1, and then we'll have subtract 7 ln 1, which is actually just 0. This term, ln 1, just goes to 0, so that will not affect the result at all. But we do have that minus 1 from the second grouping. So when I subtract that from my constant of 9, it looks like we'll have 8 plus the 7 ln 3 to finish that one off. 8 plus 7 ln 3. And just to get a decimal, let's maybe just evaluate this and just see what we've got. 8 plus 7 ln 3, just for an approximation, we should be about 15.69. We do out to a couple decimals. So you can verify that just to make sure we have the right natural log button in our calculator. Can kind of confirm that. All right, so we have the exact result and then an approximate decimal solution. Okay, let's take a look at a second one. So the first fundamental theorem problem required us to do a little bit of division first. Here, it looks like we're going to have to do some multiplication inside of our integral to get started, because we really don't know what to do with a product at this point inside of an integral. So it might be helpful to just go on the side and multiply this out and then consider our result for some power rules. So I'm going to take this 4x squared plus x, and then the x minus 2 moves over to the side and just do a product here. So we'll just use our regular foiling method for this. Nothing fancy, just regular algebra. We'll have the 4x cubed minus 8x squared, and then x squared again, and then finally negative 2x. So when I rewrite this, it looks like we can combine these two individual terms. When I rewrite my integral from -1 to 2, we'll have 4x to the third power minus 7x squared, and then minus 2x dx. Okay, this is looking good. So now we can go towards our antiderivative, so that capital F function. So going for that, we can take our antiderivative. We'll have 4x to the fourth over 4 minus, we'll have 7x to the third over 3, and then finally minus 2x to the second power over 2. Now, this certainly can get simplified here, and I think that would be a good idea. We've got a lot of constants that can simplify down. We have the 4's and the 2's here to clean it up. So our antiderivative here would be just x to the fourth minus 7 thirds x to the third, and then minus x squared. And again, this is my capital F of x function, and I'm going to evaluate this function at my two endpoints. Sometimes you'll see this evaluation bar here in the negative, the 2 and the negative 1 on the sides here. That just tells us our bounds of integration. So let's go ahead and evaluate. Again, we'll do capital F of 2 to start. So we'll have 2 to the fourth minus 7 thirds, and then 2 raised to the third power minus 2 squared. I'm just going to bracket that just to group it up. We know we're going to subtract f at our lower endpoint, -1. So we'll have to be careful with negatives on this next part. So minus, we'll bracket next, -1 quantity to the fourth, minus 7 over 3, and then -1 cubed, and then finally -1 squared. And then we'll bracket that one off too. So for this one, it's a good idea to be able to do this by hand. because we want to be able to get a exact result here. So make sure that we can do this. If you need to use a calculator as an aid, make sure we can get back to that exact result. Go ahead and take a moment to do this, and you can pause the video here, try this out, see if you can do this on your own, and then I'll be back with the solution after you pause that video. Okay, so we should have a result here of -9 if we work this down by hand. So what I ended up doing is once we simplify this line once, we'll have 16 minus 56 over 3 minus 4, and then we'll subtract. The second parenthesis or bracket would have a 1 plus 7 over 3 and then minus 1. These actually will cancel out in that bracket, and we can be canceled out there. If we distribute that negative sign to the 7 over 3, we do have a negative 7 over 3 when we're done. And so if we get all of these terms in a common denominator of 3, 16 over 1 would be 48 over 3. We can get negative 56 is already there, negative 56 over 3, and then negative 12 over 3. If we work down that result, we should get negative 27 over 3 or negative 9 for that final result. So that would be the area, again, underneath the curve from -1 to 2. So we'd have, in other words, more area underneath the x-axis than above the x-axis for this specific function. We're going to take a look at a couple of applications to finish up this section. This is taking a look at traffic flow, and we are looking at the traffic flow rate in cars per hour across an intersection is the R of t function, where t is in hours and t equals 0 is 6 a.m. So 6 a.m. So that would be our starting time. And we want to know how many cars pass through the intersection between 8 a.m. and 11 with this variable rate. So let's go ahead and consider how we would find total cars here passing through the intersection. This is very similar to kind of when we have a rate function for, say, a runner or a car, and we want to know the total distance. This is kind of measuring how much or how many are passing through this intersection at this rate over this time period. And we can walk this through an integral. So we're going to set up this integral in general is going to be from 2 points, we'll call from A to B, of our rate function. In this case, we'll have our R of t function dt. And we just have to figure out, well, what are our bounds of this integral? And then what is our rate function that describes this rate of change? So there's our rate function. So let's go ahead and do a specific integral for this question. If our starting time here is 6, let's start with those time intervals. 8 a.m. is our first time. This would be 2 hours after our starting time. So we could say that 8 is described as 2. So that would be our low endpoint. And then 11 a.m. would be described as really 5 hours after 6. And so that could be our upper endpoint. So we're really doing an integral from 2 to 5. And we always list our lower endpoint on the bottom. Now our rate function is just given to us, so we don't have to necessarily work too hard for that. And we want to take this integral dt, or with respect to time. So let's consider the antiderivative here. We'll have 300 times t, this is our variable. We can do plus 70 t squared divided by 2. And then finally plus 24 t cubed now, and then divide by that new power 3. Certainly we can go ahead and simplify this a little bit before we go to evaluate. So we'd have 300t plus 35t squared, and then plus 24 on 3 would give us 8t cubed. So we can go to evaluate this from those endpoints 5 and 2. And we'll go ahead and just evaluate this all in one. So again, this would be capital F of 5 coming minus capital F of 2, or the antiderivatives there at those points. So I'll list out how this would be calculated. We have 300 times 5 plus 35 times 5 squared plus 8 times 5 cubed. That would be my capital F of 5. Just to kind of give you different colors here. Let's just do this one in a different color just to distinguish. So next would be the F of 2. Want to subtract our F of 2. Hopefully I don't run out of too much space here. I think I might. So we have 300 times 2. And I think we'll run out of space. So let me just draw this underneath here. So we'll get these written underneath. This happens sometimes. It's all right. We'll just copy this down below. All right. There's our F of 5. Just going to get rid of this. And we'll start with our F of 2. So this would be 300 times 2. And then plus, we have 35, 2 squared. And then finally, we'll have plus 8 and 2 cubed. There we go. So you can pause the video if you want and see if you can calculate that. So if you go to find this solution in your calculator, you should find the result to be 2,571. And again, this would be in cars that pass through the intersection from 8 a.m. to 11 a.m. So in that morning hours, or at least mid-morning hours, from 8 to 11. The last application we'll take a look at also considers a rate function. This is a question concerning a company manufacturing die-cast cars, so like Hot Wheels or Matchbox cars. The rate of production in cars per hour can be measured as a function of time. That's the R of t, where time is in hours and t, again, measures from 8 a.m. in this question. So t equals 0 is 8 a.m. So if I wanted to set up an integral for this second question, we can again consider what are our bounds. 3 and 6 are the times, p.m. here. And if I start from 8 a.m. to 3 p.m., that first time interval looks like it's going to be about 7 hours. If we go from 8 to 3, this would be 7 hours. In other words, 3 p.m. goes to t equals 7. And then that would mean that 6 p.m. is equivalent to, looks like 10 hours, because it's almost going to be two less than 12 hours around the clock. So we're going from 7 to 10 for our bounds, and we're using our rate function negative t squared plus 20t, and then minus 30 dt. So let's go ahead and take our antiderivative and then see if we can simplify our result using the fundamental theorem. We have negative t cubed divided by 3 for the first term, plus we have 20t squared over 2. And then finally, if we have a constant, negative 30, this negative 30 can just be negative 30t, because we really have t to the 0 power to start with. So to put this together again, we want to evaluate this function at 10 and at 7. If we want to simplify this, we'll just do this in place. This would be just 10t, and I think that's the only simplification to make here. So we'll go ahead and evaluate again from 10 to 7. We'll evaluate from 10 to 7, and I'm going to go underneath here, f of 10 minus f of 7. I'll learn from the last problem. And we'll start with that f of 10. So we have negative 10 cubed divided by 3 plus 10 times 10 squared minus 30 times 10. So there's my f of 0. And then we'll subtract the f of 7. So we have negative 7 cubed divided by 3 plus 10 times 7 squared. And then finally, we have negative 30 times the 7. And you can also take a moment here if you'd like to solve for our final result here, if you want to pause the video. So the result for this integral should be 201, and these are going to be, again, die-cast cars. So that's the number of cars that are produced between 3 p.m. and 6 p.m. 210. So a follow-up question would be, well, how many die-cast cars are manufactured each hour on average from 3 p.m. to 6 p.m.? Well, if we have 201 die-cast cars over the whole 3-hour time span from 6 to 3, really there's 3 hours here that pass through. And so on average, we could just take a simple average here of our total cars produced and divide by that 3-hour interval. And if we do so, we should get 67 cars are produced per hour here on average. So this is I guess an average rate of cars over this interval. It would not be an instantaneous rate of change anymore, but this is again just going to be a 67 cars per hour that are going to be produced on average from 3 p.m. to 6 p.m. So this wraps up this lesson with our antiderivative rules and a few fundamental theorem of calculus problems here. Thanks for watching this video with us, and we'll have another video on this lesson coming up soon, so you can take a look at the playlist to see that. So thanks for watching, and I'll see you in the next one.